for point charge, we said that there's an electric field around it at any point. The electric field direction is away from the charge if the charge is positive, toward the charge if the charge is negative, and its magnitude is given by this formula. And then we said that if you have collection of charges, then you do superposition. And then we said that if you have a charge distribution and you want to find the electric field at any point, you take a small piece of that and calculate the electric field of that small piece, which is dE, and then the distance r, the charge dq, E is integral of dE, which, because it is a vector integral, you have to split it into x component and y component separately, and then write E total x equals the integral of dEx, and the total y component is integral of dEy, because of vector summation. If you have z component, again, the same story. Then we applied this to some different situations. For example, if you have a line of charge that has a uniform linear charge density of lambda, and you are at a distance y to that line somewhere, and we can write that the electric field at that point in terms of these two angles and lambda and y. Let's say this is theta 1, this is theta 2. Theta 1 and theta 2 are from perpendicular direction, counterclockwise. So in this case, theta 2 is positive, theta 1 is negative. And the electric field has two components. At this point, Ex is k lambda over y times cosine theta 2 minus cosine theta 1, and Ey is k lambda over y sine theta 2 minus sine theta 1. And then if you apply it particularly for infinite line of charge, then the electric field has only perpendicular component. It will be 2k lambda over y. And the parallel component to the line will be 0. That will be, in this case, of course we have a coordinate axis here, x and y. And then for a ring of charge q on the symmetry axis at distance z to the center. For example, this is distance z to the center on the symmetry axis, and then the radius of the ring is r, and the charge is q. At this point, distance z, the electric field is like this. E will be sigma over 2 epsilon naught times 1 minus z divided by square root of z squared plus r squared. Again, z is that distance from the center, r is the radius of the disk, sigma is the uniform surface charge density over the disk. And then when the radius of the disk becomes infinite, you see this part goes to 0, then you get E equal to sigma over 2 epsilon naught. That's for infinite plane of charge. So for infinite plane, E becomes sigma over 2 epsilon naught, and this is the magnitude. The direction is directly away from this plane if the plane is positively charged, and toward the plane if the plane is negatively charged. It's a uniform field and doesn't depend on the distance. Another situation where, so this arc is 2 theta naught. You want to see what is the electric field of this if it has total charge Q, what is the electric field of that at this center? Again, we're going to integrate. You have to take a little piece of that with charge dq, find the electric field of this little charge at this point. This is dE, created like that. Directly away from it if the charge is positive, or each one of these cases, you reverse the direction if the charge is negative. We talk about positive charges. So let me take this as x-axis and this as y-axis. Ex will be integral of dEx, which is integral of dE magnitude times cosine of this angle theta. Right? And now I need to write everything in terms of some variable. I think it is best to write everything in terms of the angle because this is a circular symmetry kind of. We can write everything in terms of this angle. So let's say this makes an angle d theta around here. So I'm terrible at drawing things. If this subtends an angle d theta and it's at angle theta, what is the charge in terms of d theta? What is dq in terms of d theta? If the total charge is q and this angle is d theta, how much charge is in there compared to this whole thing? If the total charge is q and the total angle is 2 theta naught, and the angle of this is d theta, what is dq? Can we say dq over d theta is equal to total q over 2 theta naught? The same ratio if the charge distribution is uniform. The charge is proportional to the angle, right? So dq is q over 2 theta times d theta. 2 theta naught times d theta. So that's dq, and dE. And for this one, the distances are, you have k dq divided by r squared. Right? And that's dq. R is constant, k is constant, so we have everything. And we have to also put cosine theta, because everything should be in terms of theta, cosine theta is fine. So say Ex is equal to integral dE, which is k dq divided by r squared times cosine theta. I now replace dq by this value and integral k over r squared. Dq will be q over 2 theta, theta naught times d theta times cosine theta. And the integral is over theta. Theta will go from theta naught to negative theta naught, right? Or if you're looking at here, like negative theta naught to theta naught. And we need to take all the constants outside. What is constant? With respect to theta 1, once you move this dq around, what changes? K stays the same, r stays the same, total charge stays the same, theta naught stays the same. So all of these come out. Ex will be k q over r squared times 2 theta on r. Then you have integral of cosine theta, d theta, from negative theta naught to theta naught. And then cosine theta, integral of cosine is sine. It will be sine of theta naught minus sine of negative theta naught, which gives you 2 sine theta naught. So dx will be kq over r squared times 2 theta naught times 2 sine theta naught, because it is sine theta naught minus sine negative theta naught, which is like 2 sine theta naught. The 2 cancels out, and the result will be this. This kq over r squared times sine theta naught over theta naught. And remember that this, when you have theta naught itself, in calculation, it has to be in radians. Okay? This result is simple. It's kq over r squared. It's that point charge formula, but multiplied by sine theta naught over theta naught. And remember that theta naught is half of the arc. What will be the result for the complete circle, if the circle was complete?
2
What is theta naught in that case? The
Oh.
theta naught is half of the arc, right? How much is that for a complete circle? Pi. And sine of pi is what? 0, right? So it should be 0, and you expect it to be 0. If you have a complete circle at the center, you have charges, electric field in all directions, they cancel each other out. You get 0. If you have this arc shrunk to 1 point, what is theta naught? 0, right? All right, so when theta naught is 0, this should give you the result for point charge. Does it do that? You know that when theta naught goes to 0, limit of sine theta naught over theta naught is what? In calculus, limit of sine theta over theta, when theta goes to 0 is 1. Right? So this becomes 1. So it gives you the result for point charge. So what is EY in this case? EY will be dE times sine theta. And integral sine theta d theta from negative theta naught to theta naught. What is this integral? Sine is an odd function, right? When you integrate over a symmetrical interval, you get 0. And you should expect that, because when you add all the contributions from these, you add all of these dE's add up, they don't create any y component. So EY is 0. But usually you have a quarter circle or something, or you have an arc of a circle, and there's no coordinate system. This x component is actually directly away from the center. So if you have an circular arc, the electric field is directly away from the center of the arc at the center if the charge is positive, and directly toward it if the charge is negative.